Hey guys. Alright, so yes, unfortunately, you probably have two videos tonight. You will just have to live. I will try to make them as short and concise as I possibly can. So here we go. This first one is over the chemistry of life. So, probably thinking, Miss Courtney, you probably fell and bumped your head because this is definitely AP Biology. Yeah, but like I've been telling you forever, all of the sciences are interconnected, especially chemistry and biology. One can't stand without the other. And chemistry is definitely the foundation of biology. Chemistry is all about reactions and how different elements and different substances and compounds and mixtures react when they're placed in different circumstances. Biology is all about reactions as well. If you think about photosynthesis and digestion and respiration, all of those things are reactions, and they depend on a lot of those elements that we take for granted. Even our bodies are built out of certain elements. So technically, there would be no biology if there were no chemistry. So that's why you need to know this. Here we go. So, for a biologist, there are only a couple of elements that are very, very essential and very, very important. So I need you to know these. They are hydrogen, sodium, magnesium, potassium, calcium, carbon, nitrogen, oxygen, phosphorus, and sulfur. Of all of the elements on the periodic table, those are the most important to us. So, give you a little refresher. The elements are arranged in the periodic table based on their number of protons or their atomic number. The periodic table is divided into periods, which go from left to right, and they're also divided into groups or families, which go from top to bottom. Elements in the same column or the same group or family have the same valence electron number and similar chemical properties. Excuse me. Why is this important? Well, valence electrons are the whole reason that chemical reactions take place. So it's important you know where certain elements are found and how many electrons they have. Are they going to donate those electrons to someone else? Are they going to take electrons from another element? Or are they going to share those electrons together? Okay, right here, sorry you can't see, but right here, there should be a graphic. It's not that special of a graphic, so we're just going to continue like this slide was supposed to look this way. So chemical reactivity depends, like I just told you, on those electrons in an atom, especially those valence electrons. So atoms tend to have either a complete shell or a partially filled shell, okay? If they're partially filled, they're either going to try to get filled by getting electrons from someplace else, or they're going to give away the electrons they currently have. In some circumstances, they might share their electrons with someone else so that they can both be stable. When I say someone, I really mean another atom of an element. So it's this condition up here that drives chemical reactions and creates bonds. Biology is all about the creation of those bonds and sometimes the breaking of those bonds as well, depending on what we're talking about. So there are lots of different kinds of bonds, but the important ones for a biologist to know would be the fact that bonds are divided into weak bonds and strong bonds. There are lots of weak bonds, only one real kind of strong bond. So our weak bonds would be hydrogen bonds, and hydrogen bonds are pretty much an attraction between a positive and a negative. Then we have hydrophobic and hydrophilic interactions. That's just interactions with water, how water interacts with itself or other things interact with water. We have van der Waals forces, which are very, very weak, just minor attractions of one part of a substance to another or one part of a compound to another. And then we have ionic bonds where one element is going to give its bonds completely to another. Our strongest bond would be covalent bonds, and in covalent bonds we are sharing electrons. So I'm not giving you my 4 and you're not giving me your 4. We are sharing our 4 electrons respectively so that we both have 8 electrons collectively. so let's talk about some of these covalent bonds. There are two main kinds. The first one is called a non-polar, covalent bond. So hopefully you're familiar with the word polar. It means that you are partially negative and partially positive on either side of your atom. So if you're a nonpolar, it means you're not partially negative or not partially positive. So in a nonpolar covalent bond, a pair of electrons are shared equally. You both have equal rights to these electrons, and they're shared between two atoms. So an example of those would be hydrocarbons. Anything that has carbons and hydrogens attached are considered hydrocarbons. These nonpolar bonds are very, very stable and very balanced, and for that reason, they make very good building material, especially for biotic bodies. The other kind of bond is called a polar covalent bond. Now, if you look at the picture real quick, this is water, and water is always known as a polar molecule because it is. Look at how big that oxygen molecule is in comparison to the hydrogen molecule. Because the oxygen molecule is bigger, it exerts greater attraction, greater affinity for the electrons that it is going to share with these hydrogens. So those electrons, which technically would sit right here and right here, those would be pulled in closer to the nucleus of the oxygen because it's a bigger molecule. So this creates uneven sharing or unequal sharing, which is why this molecule is polar. Note that it is slightly negative on this end and slightly positive on that end. So in polar covalent bonds, we have an unequal sharing of electrons between two atoms. Our classic example, like I said before, is water. Okay, so all this means is that oxygen has a stronger attraction for the electrons than hydrogen. And another way of saying it is that oxygen is more electronegative. Hopefully you remember that from chemistry. And it's because of this electronegativity of oxygen and this natural polarity of water, water has a lot of interesting properties, which we are going to explore a little later on in this video. Okay, hydrogen bonding. So polar water creates molecular attractions. And a lot of these attractions are hydrogen bonds, hydrogen bonding. It is pretty much an affinity or an attraction between the positive hydrogen in one water molecule to the negative oxygen, in another water molecule. Now, while it is a very weak bond, it is one of the most common bonds in biology. Without hydrogen bonding, you wouldn't be here because your DNA wouldn't hold together. Or it couldn't split apart when it needs to. So it's a good thing that it's a weak bond. All right, so that's it about the chemistry part for a little bit. Now let's talk about some of these interesting properties of water. So you have to remember that the majority of life occurs in and around water. Even our bodies are about 71 to 75% water. It's important that you understand how it works. On a cellular level, your cells are immersed in water, so their properties become important for life. So like I said before, water molecules create hydrogen bonds with each other because of their natural polarity. And again, that's just where the positive hydrogen is attracted to the negative oxygen on an opposite molecule. This creates what we call a sticky molecule. So if you've ever looked at the meniscus in like a graduated cylinder, for example, know how it creates that curve? Well, one of the reasons there's that curve like this is because water is a sticky molecule. Those water molecules are being attracted to the sides of this graduated cylinder. We'll explore that in some more detail in a bit. So water is known as the elixir of life. These are all the properties, and I'm going to step through them one at a time so you don't need to get them down all now. Here we go. The first property is the ability of water to be cohesive and adhesive at the same time. It's one of the reasons that you are able to drink out of straws. It is one of the reasons that water can support the weight of certain animals, like water striders, which is what I have pictured up here in the corner. So cohesion is hydrogen bonding between water molecules. So water bonding to itself. And that's that whole sticky molecule that we were talking about. Because the water is bonded to itself, it creates like a mat. Okay, and that's where surface tension comes from. So it's the surface tension that is supporting the legs of this water strider. It's literally pushing on it because the water has laid down itself like a mat because they're all attached to each other. It's the same reason that we are able to pull liquids up through a straw, not a straw, but a straw. It's the same reason that trees can pull water up from their roots all the way to their leaves, even though their leaves might be 200 feet off the ground. It's because the water is literally linked to each other. So I want you to imagine that in class I have you all stand and you link arms, and then I link arms with whoever's at the front. If I move, because you're linked to me, you move. And because someone else is linked to you, they move. And everyone moves because we're all linked up. That's how water behaves when it's cohesive. Adhesion means that there's hydrogen bonding taking place between the water and some other substance. So like the meniscus, like I was telling you about, like right here, this water is creeping up the sides because it's literally attached to the side of that glass or plastic graduated cylinder. If you've ever used a paper towel to clean up like a spill, a liquid spill of some sort, you notice when you put it down, you can see the water radiate from wherever it's touching the paper towel until it's kind of spread out evenly. That's another example of that adhesion. It's just the water molecules literally climbing up or across whatever surface they're in contact with. So, how does water get to the top of trees? Well, I just kind of explained this a little bit. So if you look at this part of the picture right here, the water's in the ground, as you know. It is going to move via osmosis into the roots out of the soil. Once it gets into the soil, it's going to be in a little straw-like compartment called a vascular tissue, in this case xylem, which is kind of like huge straws or veins that lead from the ground all the way up to the top of the trees. Once it is in this xylem, it is going to do both cohesion and adhesion to link to each other and also to link to the xylem. But here's what you have to remember. The leaves are exposed to sunlight. So as the sun creates evapotranspiration or transpiration, the water is moving out of the leaves, that water molecule that just left the leaf still pulled on the molecule that was attached to it. That molecule pulled on the molecule attached to it, and it just kept going. So as that one molecule left the leaf, all of them moved up the tree. And that's how water gets from the roots up to the leaves. Okay, number 2, water is the solvent of life. Because water is polar, because it's slightly positive on one side and slightly negative on the other side, it's a good solvent. It can break up solutes and kind of compartmentalize them, like prevent them from getting back together, thereby creating solutions. So if you look at this picture, this is the classic salt and water picture. All the red dots represent the water molecules, and the little yellow dots represent sodium, and the big green dots represent chlorine. Well, this is literally how water works. When you drop salt in water, those water molecules start pushing their way through the sodium molecules and the chlorine molecules. Notice that sodium is positive, so what water does is it surrounds the sodium with its oxygen end because oxygen is negative. The positive sodium is attracted to the negative oxygen. Chlorine, which is negative, gets surrounded by the hydrogen end of the water molecule because those are positive. The negative chlorine is attracted to the positive hydrogens. Because the water molecules are literally in between sodium and chlorine, they can't go back together, which is why if you boil the water away and you evaporate these molecules, the salt reforms. Okay, what's dissolved in water? So here are these two terms that I now need you to learn, the terms hydrophilic and hydrophobic. Hydrophilic means that a substance has an attraction to water. That makes it polar. So if you are hydrophilic, you are attracted to water, you are polar. The other term you need to learn is hydrophobic, which is the opposite. These things do not dissolve in water. So hydrophobic substances are not attracted to water, they are nonpolar. In science, we have the term that says like dissolves like. So to dissolve two things together, they both need to either be polar or nonpolar. When you add a nonpolar substance to a polar substance, they don't dissolve. Think of oil and water. Oil being nonpolar and water being polar. Okay, the special case of ice. Now, most substances are more dense when they're solid, which means that they sink, not necessarily float. Water is very different, however. Ice blocks actually floats, so ice is less dense than liquid water. Solid water is less dense than liquid water. And it's because hydrogen bonds form crystals. They have this crystalline structure. So because they're all spaced out, it creates air pretty much, which makes the substance lighter, making it able to float. This is highly important to most marine and aquatic life that live in areas that get really cold. So because ice floats, oceans and lakes don't freeze solid, which means, well, a couple of things. One, the ice is going to act as an insulator for the water below. Now, I know you're thinking, okay, ice is cold. How is it going to keep water below it warm? Well, it's acting as a barrier. It is preventing all of the cold air and actually the warmth of the water from leaving because the surface is all covered off. Okay, so it acts as an insulator. Now, because that water is warmer, it means that anything that lives in that water can probably survive the winter. Now, let's think of the opposite scenario. If ice sank instead, ponds and lakes and oceans would freeze solid every single winter. They would only thaw in the summer, and even then, it would only be just the first few inches. So nothing would really live there. The other thing, or other good thing that ice floating creates is what we call seasonal overturn of lakes. So over time, the nutrients within lakes tend to sink all the way down to the bottom. So as the seasons change and the ice melts and then it freezes again, we have what we call cold water cycles. And they pretty much help to churn up the nutrients within that water, allowing everyone to get an equal chance of being healthy because the food we eat has nutrients in it. Okay, specific heat. Water resists changes in temperature. It has a high specific heat, which means that it takes a lot of heat to heat the water up. It takes a lot of energy to heat the water up, that too, but it also takes a lot to cool it down. So because of this specific heat, water actually moderates the temperatures on Earth. A lot of people think it's like our wind. It's not. It is the water that regulates the temperatures that we feel on the land. So if the water is hot, the wind tends to be hot. If the water is cool, the wind tends to be cool. Heat of vaporization. Excuse me. So water is one of those substances that can exist in multiple phases. So as we're aware, when it's solid, it's ice. And then it starts to melt, and we have this weird phase in between where we're some ice, some liquid water. And then we have a period of time where we're all liquid. So literally we can be liquid from about 0 degrees or maybe a little above 0 degrees all the way to 100 degrees. And we have to get to at least 100 before we're going to start losing water in the form of a water vapor. So vaporization happens at this stage right here where we're still kind of liquid, but we also have some gaseous water. And then higher than 100, we're going to be pure water vapor. If you think of a pot boiling, you see steam coming off of the pot. Well, that is the water vapor. Well, organisms rely on the heat of vaporization to remove our own body heat. That's why we sweat. That's why animals pant, because they're using that evaporative cooling to cool down their system, to cool down their blood. So if you think about it, if you ride your bike and you're sweating, you don't really feel as hot because A, you're sweating, and B, the wind is moving against your body on that sweat, which cools you off even faster. Okay, ionization of water and pH. Water has the ability to ionize, which means that the hydrogens can split away from the water molecules, leaving just hydroxyl ions or OH ions. So if your H pluses and your OH minuses are equal to each other, water has a neutral pH. If you have more H pluses than you have OH minuses, water is acidic. And if you have less H pluses than you have OH minuses, then water is basic. So as you know, acids and bases are ranked on a pH scale. Anywhere between 1 and 6.99, you're acidic. If you're at 7, you're neutral. And 7.1 through 14, you are basic, or you're an alkaline pretty much. All of this pH scale is based on the amount of hydroxide ions that are present. How many H pluses do you have? Right? So our pH scale is what we call a factor of 10, or a tenfold change in the concentration of hydroxide ions. And I'm sorry, it's kind of like shifted around on you, so it looks kind of weird, but you get the point. We'll go over this in class in a little bit more detail, so I'm going to skip on. Okay, buffers and cellular regulation. Now, most cells like to be at a pH of just about 7. You make it more basic or more acidic than that, and the bonds can't hold together, the cell disrupts, the DNA disrupts, and you have no working cell. So pH is going to affect the shape of the molecules that you have in your cells. It's going to affect, and that shape of the molecule will affect its function. So therefore, pH affects cellular function. The way your body controls it is by using a system called a buffer system. So buffers are pretty much reservoirs of hydroxide ions. And it's like a cash in the bank, kind of. You know how you have a savings account, and if you kind of spend more than you should have and you're kind of running out of money, you can pull from your savings. Or on months where you've made more money than you anticipated, or you didn't spend as much money as anticipated, you can add to your savings. That's kind of what a buffer is. So when you need a whole bunch of hydroxide ions because the hydroxide concentration is falling or is too low, the buffer will donate some hydroxide ions. If you've made too many hydroxide ions and your concentration is rising, then the buffer can absorb that extra hydroxide ions. All right, so hopefully this made sense and you will be okay with it. Let me know if you have questions in class. One more video. See you guys.